MIT researchers have developed a new method to 3D print mechanisms that detect how force is being applied to an object. The structures are made from a single piece of material so they can be rapidly prototyped. A designer could use this method to 3D print interactive input devices like a joystick, switch or handheld controller in one go. To accomplish this, the researchers integrated electrodes into structures made from metamaterials, which are materials divided into a grid of repeating cells. They also created editing software that helps users build these interactive devices. Because metamaterials are made from a grid of cells, when the user applies force to a metamaterial object, some of the flexible interior cells stretch or compress. The researchers took advantage of this by creating conductive shear cells, flexible cells that have two opposing walls made from conductive filament and two walls made from non-conductive filament. The conductive walls function as electrodes. When a user applies force to the metamaterial mechanism, moving a joystick handle or pressing the buttons on a controller, the conductive shear cells stretch or compress, and the distance and overlapping area between the opposing electrodes changes. Using capacitive sensing, those changes can be measured and used to calculate the magnitude and direction of the applied forces as well as rotation and acceleration. To demonstrate this, the researchers created a metamaterial joystick with 4 conductive shear cells embedded around the base of the handle in each direction, up, down, left and right. As the user moves the joystick handle, the distance and area between the opposing conductive walls changes, so the direction and magnitude of each applied force can be sensed. In this case, those values were converted to inputs for a Pac-Man game. By understanding how joystick users apply forces, a designer could prototype unique handle shapes and sizes for people with limited grip strength in certain directions. The researchers also created a music controller designed to conform to a user's hand. When the user presses one of the flexible buttons, conductive shear cells within the structure are compressed and the sensed input is sent to a digital synthesizer. This method could enable a designer to quickly create and tweak unique flexible input devices for a computer, like a squeezable volume controller or bendable stylus. MITCSAIL, the 3D editor that researchers developed, enables this rapid prototyping. Users can manually integrate sensing into a metamaterial design or let the software automatically place the conductive shear cells in optimal locations. The researcher says that the tool will simulate how the object will be deformed when different forces are applied, and then use this simulated deformation to calculate which cells have the maximum distance change. The cells that change the most are the optimal candidates to be conductive shear cells. The researchers endeavored to make MITCSAIL straightforward, but there are challenges to printing such complex structures. The researcher says that in a multi-material 3D printer, one nozzle would be used for non-conductive filament and one nozzle would be used for conductive filament. But it is quite tricky because the two materials may have very different properties. It requires a lot of parameter tuning to settle on the ideal speed, temperature, etc. But the researchers believe that as 3D printing technology continues to get better, this will be much easier for users in the future. In the future, the researchers would like to improve the algorithms behind MITCSAIL to enable more sophisticated simulations. They also hope to create mechanisms with many more conductive shear cells. Embedding hundreds or thousands of conductive shear cells within a very large mechanism could enable high-resolution, real-time visualizations of how a user is interacting with an object.